Sorry. I know we'd love to hear our names, but we're going to do that during the course of the day. And Andrew will tell you how we do that. But I wanted to really welcome you and thank all the guys who have helped plan this, and looking forward to an exciting, is it 6 days of training here after Saturday. Enjoy. So I'll let you.
I'm going to use this
Right. Great.
for obvious reasons. Good morning. It is a huge pleasure to be here to organise this course on mathematical modelling for the control of infectious diseases, and particularly with an emphasis on vaccine-preventable diseases. This is the second of these courses that we've organised for VIMC, and the third, actually, of these courses which we have run with CIMA for African students particularly. This is the product of a much longer series of modelling courses, which I've been involved in running for over 15 years in Cambridge, with the Wellcome Trust Genome Campus and at the Vet School in Cambridge. So I am associated with VIMC, but I'm not actually a member of VIMC. I'm an associate professor at the Department of Veterinary Medicine at the University of Cambridge. I'm an equal opportunity modeler. I like to work on all animals, including humans, though. So I am very much interested in whatever disease system it is that you are working on. And one of the great things about these courses will be finding out about you and your projects, and hopefully helping to guide you down the path to how mathematical modelling might help you in your own research. What I think makes this course unique is that it is aimed at people who do not necessarily have any experience of mathematics, those from a biological background. And what we want to teach you is not the most advanced methods in epidemiological modelling, not the most cutting edge, but we want to teach you the process of how you go about modelling, okay? My role in this course is really, my key role is as the guide, to take you on a journey from where you are to the end of the course, and to put into context the detailed things that we're learning at a higher level, to understand why we're doing it and where it's going to take us. So this first introductory session is just to remind us why we're here. And I'm hoping you all know why you're here and what you're going to get, but I'm going to give you an outline of what we're going to be doing during it. Okay. So let me just first of all talk about the elephant in the room. About exactly 1 week ago, I was cycling into work in Cambridge after dropping off my daughter, and I took a bit of a tumble off my bike and broke my elbow bone. So I am not 100% at the moment, but I am very pleased that I've managed to get here in order to teach the course. But there will have to be a few accommodations just in case I am not quite able to do things. I'm feeling pretty good at the moment, so that's good. I think the only impact immediately is going to be, we have timetabled sessions for catch-up and individual supervision from 6 till 7 in the evening, which was going to be an expectation, but now will be on demand, and we'll maybe keep that for later in the week just to see how things are going, okay? Because that was mainly going to be me. But hopefully we'll be able to give you as much support as you need during the course. So we're not changing anything in terms of the content, and it's hopefully all going to go very well. So this is documentary footage of me breaking my arm last week, which I generated after the fact using an AI generation tool, which is a type of mathematical model which you might have heard about, you might be familiar with. Very clever bits of software engineering, which when we give them some form of input, here I asked it to make me a picture of a Cambridge University academic having a cycle accident on his way to work, flying over the handlebars. It generates an output, okay, which is remarkably good, okay, and it works because it's been trained on a huge amount of art, photographs, websites. I'm worried by the fact that it's got messy hair and it's got glasses. I shaved this morning, so it didn't look too similar. I get some things wrong. There's two seats, okay? Very clever, very complicated types of models, but the most interesting thing I think about these AI models is we don't really understand how they work. They are in some sense what I call phenomenological models. Okay? This image is an emergent property of the algorithms which are used by the model and the data that has been used to train it. Okay? In essence, this is what all models do. They take some form of input and they generate an output. Okay? Nobody who uses or develops these models really understands how mechanistically this works. Okay? That is not a problem if you want to generate an image. Yeah, for the purpose of modeling, it doesn't matter how this model works. Now, for science, we're fundamentally interested in what the mechanisms are, and that's because without understanding mechanisms, we can't understand the best ways to intervene and to have impacts on how infectious diseases spread. And that's why for epidemiology, we typically use much simpler and more abstract models, because it turns out even the simplest models can be very hard to understand the behavior. And that line between a simple model and a complex model comes a lot faster than you might expect. So I want to just start with the fundamental basics about the thing we are going to talk about for the next week. What is a mathematical model? Okay, if we look up the dictionary definition, a mathematical model is just a description of a process, a biological or a physical process, or a geometric object, or a concept using the language of mathematics. Okay? So you have been exposed to and used mathematical models many times in your education up until the point that you came to this course. And one of the first models we maybe get introduced to in a sort of formal sense is the model for a straight line. Okay? So a straight line is just the collection of points in a 2D plane which have this characteristic of being in a line. And we learned in school that we can describe the equation for a straight line using this, or a very similar type of equation, where the y-coordinate is related to the x-coordinate by two constants. Okay? Now, what makes this model useful is that we have a very simple geometric understanding, a mechanistic understanding of what these constants, the parameters of the straight line model, mean. So the constant c here at the end is the point where the line crosses through the y-axis. Okay? And the other parameter, which I've called m here, is the gradient or slope of the line, which again, I expect you learned you can calculate by looking at the difference in the y-coordinates divided by the difference in the x-coordinates. I hope that's all familiar. We've seen this before. Okay. So a mathematical model is just a description of something using mathematics, but there's a little bit more to it, certainly in terms of the types of models that we're going to talk about in this course. A mathematical model could be thought of as a caricature or a cartoon, a simplification of reality. Okay, this is an incredibly important thing in understanding biological systems, because biology, the real world, is incredibly complex. In fact, it's probably too complex for us to understand all of the processes that are contributing to an observed set of data in a biological population. If we simplify, we can understand the essence and identify the most important elements and mechanisms which contribute to the patterns that we see in data. So ideally, a good model is going to give a good representation of the real thing so that we can identify it, in this case as a tree, but it isn't necessarily doesn't need to capture all of the detail about what a real tree would look like or what it does. And this example is to point to this point which I've talked about already, that complexity comes incredibly quickly in mathematical models. So this is an example of a class of mathematical models called a cellular automata. Okay, so it's not really a mathematical model. In some sense, it's a computational model because we define the behavior of it using a set of rules. Okay, the first rule is we draw a single line to represent a trunk, and then at the end of the trunk we split at some fixed angle and draw two more straight lines, two branches, and then we iterate and repeat that process. Okay, and if we do this, we get this infinite recursive, what we call a fractal geometric structure, which is very similar to the type of structures and complexity that we see in real biological populations, but has been generated by a very simple model with just one parameter here. Okay? So complexity is something that can emerge from even the simplest models. So the more complexity we put into a model, the more difficult it is to understand exactly which mechanisms are responsible for a particular observation. So, mathematical models are a description of the behavior of a system using mathematical concepts or language. Fundamentally, and this is a really important quote from the great statistician Pelham Box, and a lot of people focus on the first bit, especially post-COVID, that all models are wrong. Okay? It's important to remember that, but some models are useful. And the intention of this course is to guide you towards understanding what it is that makes a useful model for epidemics. Okay. For me, I will see if you agree with me once you get to the end of the course, a good model, a useful model, is one that provides some insight into the system that goes beyond the assumptions that we use to construct it. It's very easy to make a model in some sense, yeah? If we think of any infectious disease or pick any infectious disease that you are working on, we write down all the things that are important. We'll end up with pages and pages of things, and we could make a model which describes all of that. And if we were lucky enough to run it, we probably wouldn't understand what it meant, and we wouldn't be able to estimate all of the parameters that describe all of the bits that go in. Okay? That model, I would argue, would not be useful because it hasn't got a purpose other than just describing what we know or what we don't know. A useful model then has purpose, and it gives us an insight and understanding that we wouldn't have had otherwise. It gives us something new. Okay. I'm guessing we're all scientists, one sort of another. So we're very familiar with the scientific process. Essentially, we do an experiment and we find a result. So that's great, we get some cake. And then we do it again and we find we get a different size of cake. And this is the bane of all experiments. We never get exactly the same result when we do an experiment. We get some variation. And that's why all of you in this room, if we did the selection properly, will have done some training on statistics, which we can think of as another form of mathematical model, as another family of mathematical models. Ronald Fisher, a Cambridge statistician, he described statistics, and this is something my colleague T.J. McKinley, who's joining us later in the week, he's a Bayesian statistician, he'd probably disagree with me, but he's not here, so I can get away with it for now. Statistics is the study of observational data, and it's the mathematical language to understand populations and variation in populations, and to reduce that complexity, the reduction of data, large data, into parameters. So at some point you will have been introduced to the normal distribution as a way of describing the variation when we make an observation with error. Okay, and we can characterize that in terms of a mean and a standard deviation, and then we can torture you with all sorts of statistical hypothesis tests, t-tests, to say whether or not an observation is likely to be greater than another with some variation. It provides a framework to ask useful questions. And those methods are terrific when we are considering a population which is fixed or that isn't varying over time. Now, with biological populations and with epidemics, we have another challenge in that there isn't really a concept of a fixed population. Populations are always changing, abundance is changing over time, and in order to unpick and describe those types of behavior, those types of dynamics, we need a different type of mathematical model. This is a very famous ecological time series, which has got a little bit washed out here on the screen. I apologize for that. So you can see the dots very clearly. A line has been drawn between the dots, which is a little bit faint here, but what you can hopefully see is that there's a regular pattern in this time series. Okay? So what this is, it's the number of lynx furs bought by the Hudson's Bay Company from 1821 to 1910 in Canada. And this is a really important foundational data set in ecology and in the ecology of wildlife populations. Because when this data was collated over a long period, it became evident that the variation in the lynx population wasn't random, but it had a periodic pattern with a cycle of around about 9.6 years, okay, between the peaks in abundance. And that's really fascinating, because where you see that sort of regularity, something must be driving it. There must be some mechanism which is imposing order onto this pattern, the size of the population. Okay. So what could be generating that? Anyone got any ideas? I've just remembered I should be interactive. What do you think could generate cycles in a population like this? Has anyone got any? Yeah, and could you say your name and your where you're from when you before you talk? Yeah, back there.
My name is Aminu Mohammed from Nigeria. I think it has to do with the climate change.
Okay. So this was pre-industrial. So this was 1821 to 1910. But climate, or rather seasonality in weather, is an important driver of mortality and fecundity rates. So a lot of wildlife populations have seasonal breeding. And they're more likely to die in the winter rather than the summer. So climate's probably an important part of this. But climate has a one-year cycle, more or less. So why would we get 9.6-year cycles?
My name is Gloria Butchie, from Ghana. I think predation.
Yeah?
So maybe predation is responsible for that. Prey.
That's a really interesting idea and a really important one. And a couple of early ecologists had exactly the same idea, because they knew that the snowshoe hares were predated upon by wolves, or lynx rather, and they hypothesized that that interaction between the predator and the prey could be responsible for generating the sequel, cycles and incidents. So in order to explore this hypothesis, they developed a mathematical model with some very simple assumptions. They said, Well, let's assume that the growth rate of the lynx population depends on the supply of food, so the number of hares. So, and the death rate of the hares is going to depend on the number of lynx that are eating them. So there's a balance there, okay? And in order to describe this, they wrote down a set of what are called differential equations. Has anybody here heard of differential equations before? Just a brief show of hands. Has anyone never heard of a differential equation before? All right, we've just got a lot of shy people. Okay, good. Well, I'll just assume you know it all. But differential equation sounds scary, but it's very simple. It's just saying the rate of change, so the derivative of lengths with respect to time, is going to be a function of the number of links that are dying. So this is the loss rate, a negative term. And the production rate of the links is how many links manage to interact with hair and eat them and consume them, which is controlled by this parameter P1. Okay? So this nonlinear term here comes from the fact that the number of interactions or meetings between lynx and hare is going to depend on the density of both of those populations. And we can write a similar equation for the hare, where the loss rate is now dependent on the predation rate, and there's some sort of birth rate. Okay? If we solve these equations, either analytically, can we do it analytically? Possibly. It's easier to put them in a computer. Then we can see that if we choose the parameters just right, we can get some lovely cycles and incidence of both the hare and the lynx populations, with the lynx population cycle leading the hare population. Okay? So by making some assumptions, formulating a model, we make robust predictions about what the period of oscillation should be and what the relationship between the hare and the lynx cycles would be. Okay? So this was a fundamentally important establishment, effectively, of the field of theoretical ecology. Okay? What's important to remember, though, is that these models are also wrong, in that these models do not predict the right period, and they do not predict the right relationship between the hare and the lynx. And these populations have now been studied for over 100 years. Careful experiments have been done looking at all sorts of biotic and abiotic variables, and still we don't fundamentally understand the origin of the period of oscillation of hare and lynx cycles. Okay? That doesn't matter, though. These models were still useful because they exposed how the mechanism can generate the observed patterns. Okay? Step one is understanding what mechanisms can contribute to patterns. Step two, which is the hardest part, is mapping the parameters of our abstract models to the real data. And that's where ultimately we hope to get you to by the end of this course. And this is where dynamic models, mechanistic models, are fundamentally different from just simple statistical descriptions of data or extrapolations. Okay? If we have a linear extrapolation, we can make a very firm prediction of what is going to happen, but because that model has no information about how much more likely you are to get married after you've already been married, you are not going to make a useful or good prediction. Okay? It turns out dynamic models are essential to predict the impact of vaccination in particular, and that's why we are organising this course for VIMC. And that comes down to the impact that vaccines have, not just on the protection of individuals, but on the rate of transmission of disease within a population as a whole. Okay? That's the story for another lecture now. So the predictive power of a model, though, is going to depend on being able to identify the correct mechanisms driving the behavior of the system and the quality and extent of the evidence that we have available to design and to estimate our model. Now, what I mean by estimate a model is find what parameters are of our model most relate to the data that we have. So the process of modeling, although it is an abstract mathematical exercise in some sense, should always start with data and observations. From that, we make our caricatures, our cartoon of what the population we're interested in looks like. This is my badger cattle example, because I work on bovine tuberculosis. From that model, we make predictions, and those predictions can then be checked and assessed against data. So the process of modeling is this virtuous loop between looking at data, conceptualizing, analyzing models, and then looping back to make those predictions. Okay? And most good mathematical modelers are forever trapped on this loop until finally you escape and you maybe get a good publication once in a while. So the types of evidence that we use in disease dynamic models are perhaps the biggest challenge that we have in working in this field. So if we were working in particle physics or nuclear physics, we would always have the luxury of just doing more and more careful observations, more experiments to refine our models and progress. A lot of the art and challenge of epidemiological modeling comes from the fact that sometimes we have no data. We only have opinion from experts. We have a best guess about what is important for a disease. And that is the weakest type of data that we could have, but it's a starting point. Experimental data, you might think, is the gold standard. So that's how we do most of science. It's a fundamental problem with experimental data for epidemiology, though. Anyone got any ideas what that is and why it's actually not as useful as it is in other sciences? Yeah, at the back. Yes. No, that's exactly right. So we only have one world in which diseases are spreading, and many diseases have pandemic potential or are circulating globally. Yeah? Doing an experiment on the globe is not an option. Okay? Doing an experiment on people is fundamentally unethical. You know, we get a bit further with experimental studies in animal veterinary disease because we have the opportunity to do more natural transmission studies. But even then, we are separating and looking at an artificial environment where we control a lot of the variables which are going to be fundamentally important for control. And that's why most of the time what we have to deal with is observational data from a single population, a single replicate, and we have to work out the best way of mapping our abstract ideas of how disease transmits to the type of data that we can and are able to collect. Okay, so what are we going to try and do in this course? Most of you have only limited experience of mathematics. We are not going to turn you into world-class mathematical modelers by the end of this course, okay? What we want to do, though, is to start you on the right path, to give you the tools that can enable you to become a world-class mathematical modeler and to hopefully transform the research that you're doing and how you do it. And we're going to do this from a very ground-up perspective. We're going to introduce you to the use of mathematical models. We're going to describe what they are, how they work, how to apply them, and ultimately how to estimate and fit them to data. Okay? That's a lot. Okay? As we do that, we're going to hopefully provide you with the core conceptual and practical tools that you need to develop models for your own research. So my hope is that by the end of this course, you should be able to write down, you should be able to code up, you should be able to start doing things with a model that's relevant for your own research. That's where I want you to get to. So how do we do this? 5 main topics. We're going to start by looking at the basics, a refresher of the mathematics that we need in order to build and analyze these models. Katie is going to take you through calculus, differential equations. I'm going to remind you about probability and introduce you to programming in R. Now, all of you should have some experience, or quite a lot of experience in R. You might have done some programming in R, but you might not have thought about it from a sort of computer science or a programming perspective. And I'm going to try and give you a little bit of insight there into how we think about R as a programming language rather than just as a stats package. So loops and functions are the key thing that we're going to try and understand there. And once we've got these fundamentals, we are not going to start talking about epidemic models for a bit. We're going to start with just looking at dynamic models, basic population models, and how we link them to data. Then we'll go into the theory of epidemic models using very simple compartmental models, both from a deterministic perspective, so the differential equations like the predator-prey that I just talked about, and stochastic models, a bit more realistic, about how diseases really spread in real populations. We'll then open a window into how we build more and more complex structured models, why that's important, and of course we'll spend a lot of time talking about the epidemiologist's favourite parameter, basic reproduction ratio, R0. And all of that's building towards the final part of the course where colleague TJ is going to introduce you to the fundamentals of Bayesian inference, likelihood, and how we can apply these methods to the dynamic types of models we need for epidemics data. Okay, housekeeping rules. We've already broken the first one. We did not start promptly at 8:45, but we should aim to do so. We have got regular breaks during the day, coffee break, lunch, and tea break. Do please take advantage of these, okay? Especially once we start getting into the practical sessions. I know from previous courses, people can start to feel, oh, I just need to stay on the computer, keep working, keep working. That is a road to burning out halfway through the week. It's important to have a break, to talk to your colleagues on the course, talk to the instructors, and come back to it. All of the practicals that we give you have got worked solutions. It's all online now. You should not look at them first, but they're available if you need them, okay? So you're not going to miss out on anything. You will be able to catch up, and we have space in the course to catch up. As I said, when possible, we'll have that Q&A time between 6 and 7. It does make the day very long, and I'm sure those of you that came in at 3 o'clock this morning, as well as me, will appreciate maybe not doing that today, but we will try and offer that later in the week. We'll have a celebratory dinner on Friday evening, and the course will end on Saturday after the final seminar. We are not now going to do speed networking, but that is really important. We are going to do that just before lunch, and this is how we're going to get everyone to introduce themselves to each other. So rather than just go around the room and listen to everyone, we're going to try and do this in a process where we all meet each other by having a timed amount of time with each other. Have we ever got this to work? Yeah, it works very well for about half the time, and then it devolves into chaos. But I think that is a good chaos, which will help us to bond. So I think it's a good process to go through. So that is coming up. But for now, I think we're diving straight into the maths with Katie. Katie. While Katie's setting up, I should just say, has anyone got any questions? Does anyone feel like they've signed up for the wrong course and they want to run away? Anything unclear or anything at this point? Okay, super. Yes, you can.
Here we go. Fantastic. Great. Can everyone hear me okay before I get started? Brilliant. And we'll see. Fantastic. Cool. Okay. Lovely to meet you all. It's brilliant to be here. I'm Katie Gaythorpe. I'm research leader of the VIMC. I'm also a lecturer in the School of Public Health at Imperial College London. If you're interested in talking more about VIMC and what it does, other things that we've got going on like fellowship opportunities or affiliate membership, then just let me know. I'm happy to talk about VIMC. Happy to stop talking about it as well, but if you've got any questions. So, looking forward to speed networking and understanding the projects that you're working on and how this course might relate to it. These lectures are going to be, as Andrew said, putting together some of the things that you might want to recap or remind yourself about so that we can start fitting together equations, differential equations later in the course, and so you can start building your own models. So starting off with some of the ideas behind the mathematical concepts that we're going to need. So thinking in this lecture about functions and equations. So we're going to go through what is a function. We're going to revise some familiar functions, possibly some unfamiliar functions, and how you manipulate them or put them together, especially in terms of putting together equations which we can then start to solve. And again, we'll go through some examples of equations that you might come across through the course and routes that we can use for solving them. But of course, you're going to be using programming as well, so there's times when you might want an analytical solution of things and times when you might want to simulate it in a computer, and we'll come back to that as well. So, what do we mean when we talk about a function? So we've got this line here, so a mathematical way of encoding a numerical rule. Essentially, we're writing down a relationship. And you're going to be doing this all the time for a whole number of reasons. You're going to be thinking about how an independent variable, so here we're calling it x, but often we're talking about time as the independent variable. And we're thinking about how that is influencing a dependent variable. So here we're calling it y, but it could be anything. So essentially we're writing down the relationship between something that's changing and something that depends on that thing that's changing. So later on we'll be talking about the number of infections over time. So our infections, or projecting the number of infections for a disease, might be the dependent variable, and then time is that independent variable. So a bit of mathematical terminology. So we say an independent variable comes from a domain, and the set of possible outputs comes from a range. We're not going to use this terminology too much, but if you come across it, that's what we're talking about. And then we've got a few examples here that are hopefully visible. So here we've got this kind of notation where we've got f of x. So f is dependent on x, it's a function of x, and we're saying that it's equal to 10x plus 3. So that's a linear equation there. But we can also have slightly more complex here. So here we've got g of x, so again, a function of x. G is depending on x. And now we're saying that's based on the log of base e of x. And for that one, we need to define what our domain is, just because this only makes sense for certain values of x. And we're going to come back to logs and exponentials and how we manipulate them and how we can solve them in our equations later on. Often when we're presented with an equation like this, or a system of equations, we try to get a feel for what they look like. So often we're thinking about what do these equations look like in terms of graphs. And I'm going to come back to, as we go through some of these examples here, and we're going to focus on linear, quadratic, exponential, and logarithms. And we're going to come back to what they look like as well as how we write them in terms of an equation or a function. So, let's start with something that Andrew's already introduced. We're starting with a linear function. So here, our independent variable is y. It's a function of x, it depends on x. And x plays into this equation. So we've got two constants here, m and c, so that just means they're a number. We're not expecting them to be changing. I'm going to say y as a function of x is equal to mx plus c. Okay. So we've got plenty of examples here. We could have m equal to 2, c equal to 3. We can have a negative for m. So we'll come back to how that looks in terms of a graph later on. We can have c equal to 0, and then this is a slightly simpler equation where we're saying y of x is equal to 2x. And then finally, we can have m equal to 0 as well. What we're saying with this equation is that for every change in x, we expect the value of y to increase by m. And because we've got this constant on the end c, when x equals 0, y equals c. That's all we're saying with this equation. And again, the temptation with modeling, and we'll come back to this later, is to, because we know the systems or the data or the disease that we're looking at is very complex, we want lots and lots of complexity, but often there are many components where we're using a linear relationship. Essentially saying, we've got an increment of x changing, that's going to change our y by m. So in terms of these constants m and c, we often refer to m as the gradient. And we'll come back to what that looks like. And then we say c is the y-intercept of the line. But essentially that comes back to if x is 0, y is equal to c, as this whole term disappears. Okay. So again, it's often more useful to, or it helps with the understanding to look at a graph of some of these. And I'm sorry this is so tiny. But here we've got y is equal to 2x plus 3. We've got a gradient of 2. It's positive, so that every time x changes by 1, our y increases by 2. And then we've got a y-intercept of 3, which means that when x is 0, y is 3. Okay. On the flip side, over here, we've got y is equal to minus 2x plus 5. So the gradient is negative, it's going down. That's why it looks a little bit different. Our y-intercept, so when x is equal to 0, y is equal to 5. Okay. Hopefully, all fine and relaxing. So let's bring in a bit more complexity. So again, and we'll come back to this when we're talking about developing a model, we know that there are some linear relationships, or at least if we look at a snapshot, we might have a linear relationship. So for example, mosquitoes are more active when the temperature's warmer. It's not the whole story usually. So we might want something a bit more complex, and let's look at quadratic functions as an example of that. So again, we've got y is a function of x. Here we've got, I'm going to try. Oh. Here we've got 3 constants, a, b, and c. They're just numbers. We're not expecting them to change. The thing that's changing is x. We've got an x squared term as well as an x and a constant. So now we're not talking linear. We're going to expect a curve. Again, we can think about what that might look like. We can try out different values of a, b, and c. So here we're just saying that a is 1 and b and c is 0. So now we've got y of x is equal to x squared. we can go through some of these other examples, setting essentially different constants or different values for our A, B, and C. Again, like with the linear equation, if x is 0, both of these terms disappear, and y is just equal to c, so what c is still our y-intercept. But that's only one point on the graph. Often we're more interested in what our graph or our function is doing as we get to very large values of x or very small values of x. So what's it doing as we approach infinity or minus infinity in x? That behavior is dominated by what's going on with this ax squared. So x squared is the biggest value potentially in that equation. So this a constant is quite important. And this is easier to see with the graph, but let's start thinking about it. So as x tends towards infinity, if a is positive, that means that y is going to tend towards infinity as well. So as x gets larger, y gets larger. If a is negative, as x tends towards infinity, y is going to get smaller and smaller, well, and tend towards minus infinity. Then, slightly less exciting case, if we've got a is equal to 0, again, this term disappears, we've got our linear equation. We know what that looks like. Something else we can start doing with this is thinking about roots or solutions. And when we say a solution here, we're saying, okay, what value of x makes this equation, y of x equals 0, make sense? The number of solutions to this equation depends on what we call the discriminant, and we're going to come back to this when we talk about how we solve a quadratic formula, or the quadratic equation. But let's have a look. So here we've got a couple of examples. Again, we're thinking, okay, what is the behavior? Where are we crossing the y-axis? Where are we crossing the x-axis with this? And what's it doing as we get very large values of x or very negative values of x? So here we've got y is equal to x squared minus 5x plus 6. We've got a positive constant on the x squared. So we have what we could call a happy graph, so it's a smile. So here we're saying as x gets very large, y is also going to get very large. So we can get a feel for some of the behavior just looking at these constants in the equation. On the flip side over here, we have what we could call an unhappy graph, so a bit more of a frown. Here we've got a is negative. So as x gets very large, y gets increasingly negative. And then again, because we're interested in other intercepts, so our y-intercept is just the constant c on the end, so it's 6 here, 3 here, and so on. So we can look at the equation, we can start thinking about, okay, what are the y-intercepts, what do the constants tell me? Let's look at how the behavior changes as x gets very large, and then we can start thinking about what that looks like on the graph, and we can get a feel for the function. And this sort of steps, or this process, can help you get a feel for other functions that you may be less familiar with. Okay. So another helpful one are, well, not one, a series of them, are thinking about exponential functions. So we might have something a bit more like this. So y is a function of x is equal to a e to the bx. Now a and b are constants. They could be any number. E here is a special number, so it's about 2.718. It's a rational, so the number goes on forever, a bit like pi. come back to why we like E, or not like E, but it's got some nice properties to it. But thinking more about this function and what it looks like, so we've got a couple of examples here. Again, these examples, we're thinking about what happens if we set our constants to different values. So if A is equal to 1, B is equal to 1, we just got Y is equal to e to the x. So there's a little bit of notation around this, or ways that it's described. So I said e to the bx. It's sort of shorthand for e raised to the power of b times x. You might also see it written a bit like this. So we might have exp brackets, the thing inside. And certainly when you're writing it in R, this is how you're going to be writing it. Okay, it's a similar process. We're interested about what's the behavior of this function before we start graphing it. So y-intercept here is actually a, because e to the 0 is equal to 1. We'll just come back to a few kind of rules around exponentials. If we think about that b there, that constant b, what's that giving us in terms of understanding? If b is positive, that means as x gets larger and larger, this whole function gets larger and larger. So as x tends towards infinity, y is also tending towards infinity. If b is negative, that means that as x gets very large, this whole term gets very, very small, because we've got e to a negative power. We'll come back to these rules in a moment. So we're starting to get a feel for what these might look like. They don't have roots, and we'll come back to that, because, well, one of the perks of using e at all is that we've got this nice relationship. So here we've got another differential equation. Essentially, here what we're saying, we're wanting to get some understanding of how y changes as x changes. So if we've got this differential equation, and we'll be seeing this one a lot as we work through looking at more and more complex differential equations and models, we're saying that to understand how y changes with respect to x, it's changing by by. So when we solve this, which we will later on, I think tomorrow, you can see how e to the bx arises as a solution. So it comes up quite a lot. It's quite useful. Okay. As with all of these things, it's a bit easier to see on a graph how it's behaving. So here we've got y is equal to e to the x, or exponential x. We're crossing the y-axis at 1, so our a here is 1. And because we've got a positive b, we've got this exponential growth. So as x gets very large, y gets very large. Again, on the flip side, here's another example. Here we've got y is equal to 4e to the minus x. So we've got that 4 there, which means we're crossing the y-intercept at, the y-intercept is 4, we're crossing the y-axis at 4. And as x tends towards infinity, typo there, y is getting very small, so it's approaching 0. It never quite reaches 0. These equations don't have any roots, but it's approaching 0. It's getting very, very small. Okay. So we've looked at exponentials. They're very helpful. Hopefully we'll convince you through the course that they're helpful for building more complex functions. So here's an example. You'll be seeing this a few times as well. Here we've got y of x is equal to 10 over 1 plus 99 e to the minus x. So it's It looks only a bit more complex than the things that we've been seeing previously, but you can see we get quite a nice, interesting curve going on. This might look familiar in terms of dose-response curves, or if we've got something limiting in terms of our population, we might have initial population growth, and then that will kind of level off as we get to the limiting capacity. Again, we'll look at what that looks like tomorrow morning, I think. So we can put them together, still in fairly simple equations, and build something complex and hopefully more useful. Okay. So we've thought about exponentials. We can also think about sort of the opposite of exponentials, logarithmic functions. So they're the reverse of exponentiation. So here, if we've got x is equal to log base a of y, that means this implies both ways that y is equal to a to the x. That's what we're saying when we mean the reverse of exponentiation. A here is the base of the algorithm. It's what we are raising to the power of x. Okay. Again, we can look at some examples. So log base 2 of 8 is 3 because 2 to the power 3, 2 cubed, is equal to 8. So we can move from one to the other. And that's going to help us solve equations later on. Another example is if we've got log base 10 of 0.001. That's equal to minus 3 because 0.01 is 1 over 1,000, or 10 to the minus 3. So log base 10 is used quite a lot. It's helpful in calculations. It's sometimes used in figures if you've got things changing over magnitudes. We also use a lot log base e. This has got some lovely properties when we come to differentiation. Mathematicians fundamentally try and get to the easiest way of writing things out. So we might write this as an ln, but that's why we use log base e, because it's going to make some of our calculations a bit easier. So yeah, log base e could also be written ln, or sometimes called natural log. So we've got some equations. We've gone through what they might look like. We've got kind of different forms of them: quadratic, exponential, logarithm. We're going to add an extra line on here in terms of thinking about solving equations, because we could have simultaneous equations. That means that one of our equations depends on another equation. So it's not just one that we're thinking about solving, but maybe 2 or 3 or hundreds, depending on the problem. Hopefully you can see why it might be useful to solve the equations, because usually we're putting together, okay, we've got this relationship. I'm going to keep mentioning mosquitoes because I work a lot on yellow fever, but if we think about mosquitoes, generally more active with a higher temperature, so we could start by saying there's a linear relationship between activity of mosquitoes and temperature. That's a very simple assumption, but maybe we start there and then think about how we might improve that assumption later on. So we've thought of our equation or a relationship. We now want to solve it. We now want to start using it. So I mentioned earlier on with talking about quadratic equations, we've got something called a discriminant, and we've got this quadratic formula. So it's very nice. Here, if we've got an equation of the form a to the x squared plus bx plus c equal to 0, we've got this nice formula here. You may have seen plenty before, which will help us write down the solution for it. What we're getting when we solve these equations are the x-intercepts. So where is it crossing that x-axis? So either with our happy graph or our unhappy graph. And as I mentioned before, a lot of quadratic equations have two solutions. So here we've got a plus minus. That might give us two solutions. They might just have one, though. And they might have no solutions at all. So we'll come back to some examples on that, because I think that makes it a bit easier to see what's going on. So, long story short, if we've got a nice quadratic formula, quadratic equation like this, we've got this quadratic formula that's going to help us out. We don't need to derive this from first principles, because someone's already done it. But just for your reference, if we're thinking about where it comes from, let's say we start with our generic quadratic equation here. We can factorize this. So I'm pulling a outside of the brackets and just rearranging this. You can do something called completing the square, where we're thinking about what x plus constant would we need to make this part make sense, and then we do a little bit of tidying up, so we add a minus b squared over 4a squared. Again, you don't have to do this. You certainly don't have to do it every time. We can just use the results. But once we've done this, we can rearrange to get our x essentially on its own. So the aim with kind of factorizing and rearranging this is we want an equation for x in terms of all of those constants that we've got in our model. So what we end up with is x is equal to minus b plus or minus, so again, thinking two solutions potentially, this square root b squared minus 4ac, we'll come back to that, all over 2a. So if you ever have to solve a quadratic equation, you can go straight to this formula to help you out. Let's think about an example. So here we start with our general form, but we've got particular constants here. So a is equal to 1, b is equal to minus 5, and c is equal to 6. We saw a graph of this earlier on. It's a happy graph. We've got a quadratic equation, so we can jump straight in with our quadratic formula. We put these values of a, b, and c into our quadratic formula. And then we end up, once we simplify it down a bit, to having 5 plus or minus 1 over 2. So here, we've got two solutions. X is equal to 2, or x is equal to 3. These are the values of x where this equation makes sense. Okay. So in this case, we've got two solutions, and you can see that if we plot it as well. So here we're crossing, I'll go back to the original one. It's ambitious. Yep, here we've got our happy graph. This is exactly the same equation, and we're crossing the x-axis at 2 and 3. We've got our two solutions. Okay. And now to get back. Here's another equation. Essentially, we're thinking about different... Sorry, go on.
Yeah, sorry. I know this will sound like a silly question.
No silly questions.
When you're solving quadratic equations,
Yeah.
A, B, and C always given, right? Because the one you just solved were given, right?
Yes. Yeah, so this is thinking about the situation where you've written down your quadratic equation and you've got your values for A, B, and C. Either it's something you estimated from data or they're just as part of it. Yeah. Great. So here's another example. We use the same formula to solve it. So here we've got a equals 1, b is equal to minus 2, and c is equal to minus 1. Always remember the negatives. I mentioned earlier that there's something else that we can get to before we even start solving this equation, and that's thinking about this term, this b squared minus 4ac. So this pops up in the quadratic formula here. And it's kind of to the right-hand side of that plus or minus. So this is why it dictates whether we've got two solutions, one solution, or no solutions. So in this case, if we think about just this part of the formula, b squared minus 4ac, we can substitute in our values of the different constants. So b squared here is -2, and a is 1, and c is -1. We substitute those in, and the value of our discriminant is +8. Okay. If this is positive, we get 2 roots, because we're taking a square root of a positive number. Okay. Let's look at another example. So here, we've got a very similar equation, but our b is -2 and our c is 1. When we substitute that into our discriminant, our b squared minus 4ac, it's equal to 0. So now the whole term to the right of that plus or minus is 0, and that means we end up with one solution. So it just touches the x-axis in one place. Okay. And then finally, we might have something like this. So again, a similar quadratic equation, but when we pull out those constants b, a, and c and put them into our discriminant, we get -8. So when we take the square root, unless you want to get into complex numbers, which we don't on this course, you don't have any solution. So it's not touching the x-axis. So before you jump into the full quadratic equation solution using your quadratic formula, you can get a bit of information about what it might look like just using this discriminant term as well. Okay. So we've got our quadratic formula. Great. Someone else has worked it out. Great. We're convinced that it worked because we've looked at the proof. We're not going to go through all of the proofs of everything, but it's got some interesting characteristics, and particularly that discriminant term is going to help us get an idea about what this graph might look like and how many solutions we can expect to get when we solve that equation. Okay. So that's quadratics. Oh, before we move on, something to remember is when we've got our equation like this, we might have the situation where c is equal to 0. So we could have something that looks a bit like this. Y of x is equal to x squared minus 3x. No constant c. The temptation when you're solving this is to say, okay, well, I'll set it to 0. We've got x squared is equal to 3x. I've done a bit of rearranging. That means x is equal to 3. But the problem with that is that we miss a solution here. So the issue comes when we go from this step to this step, because essentially we've implicitly assumed that x can't be 0, but it could be. So always be conscious of, if you're solving an equation like this, where we don't have that extra constant, we might have a solution of x is equal to 0. So sometimes we could say, well, maybe that's, instead of rearranging like this, we factorize. So we take x outside of the brackets, we end up with x brackets, x minus 3 is equal to 0. It's a bit easier to see that there's a nice solution of x equals 0, and there's a nice solution of x equal to 3. Okay. So one thing to remember. Again, if you put this into your quadratic formula, you would end up with the correct answer, just with your c equal to 0. Cool. So that's quadratics. This is like a whistle-stop tour or a fast review of these functions and some of the tools that you might use to start manipulating them. If you're thinking this is too much all at once, don't worry. You will have the lecture slides. We will go through these 3 different lectures on the course. We'll be coming back to some of these concepts. You'll get quite comfortable, hopefully, manipulating these functions. With exponentials and logarithms, there are a few things to remember in terms of how they behave, essentially rules to learn. So for exponentials, we've got rules around how we can manipulate them based on how they're set up. So for example, we've got c to the a plus b is the same as saying c to the a times c to the b. So again, here we've got the same base, but with different powers. If we had different bases, we couldn't say this. If we've got a negative in the power, that's essentially the same as saying dividing by that. So c to the a minus b is c of a times b is the same as saying log to the base c of a plus log to the base c of b. Again, we can manipulate this by, well, we can think about what happens in terms of having a division there, so we get a minus sign. We might have another power going on. But essentially, these rules help us manipulate the equations that we're trying to solve so that they're easier for us to solve. Again, the aim of a lot of mathematics is to make things more straightforward or easier to write down. Another key thing to remember is anything to the power 0 is 1. And as a result, log base a of 1 is equal to 0 for all a. So again, just some rules to bear in mind as we start working with equations later on. So let's start looking at it. We've got an exponential equation. We'll have a few of those coming up. Because logarithms are the reverse of exponentiation, we're going to be using those at some point down the line. But before you jump into using logarithms, it's safest to arrange things so you've got something nicer to work with, essentially. So we want something of the form a to the power b is equal to c. Easier to see in the example. Let's have a look. So here we've got something where we've got 5e to the x is equal to 10e to the 2x. Okay. We're aiming to have all the exponentials on one side and everything else on the other side. So what we do is we take our e to the x over to the other side, and we take our 10 over to the left-hand side. Left as you look this way. Okay. We know now, because we've got our list of rules, that we can rearrange this to be a bit tidier. So we've got e to the 2x divided by e to the x. It's the same as saying e to the 2x minus x, all in the power there. And that simplifies down to e to the x. So now we've got our equation in a nice form. We've got e to the x is equal to a half. And that's where we can jump in with our logarithm. So again, the reverse of exponentiation. So we've got log base e, or natural log, of a half is equal to x. And we've solved our equation. Okay. And then if you want a numeric value of that, you can put it into R or Wolfram to get a value for that as well. Okay. Last up on this is thinking about the situation where we've got more than one equation. So again, if we're thinking about describing a disease or a population, often one population might need one equation, but more likely we're thinking about a system of equations. We've got a couple of things going on, or a few things going on, and they all relate to each other. We might have, as a starting point, a pair of linear, kind of simultaneous equations, and there's two basic methods to solving them. With this, you get to the same place with the different methods. It's just really what you feel more comfortable with. My preference is substitution, but you might get on well with elimination. It's up to you. There's other, other approaches. We will come back to solving systems of equations as well. So again, it's easier to see with an example. Here we've got our two equations. So 2 is equal to 2x minus y. That's what we're calling equation number 1. And then we've got 1 is equal to x plus y. And that's our equation 2. So, two methods. Let's go through the first one, elimination. So, again, there's more than one way to do this, but if we think about what's the aim of elimination as a method for solving these equations, essentially we want to get rid of one variable so we can understand the other variable. So if we take here our equation 2, if we multiply this whole thing by 2, we can do that. As long as we make sure we multiply left and right hand side of the equation, that's fine. If we multiply this whole thing by 2, then we end up with a 2x. Great. So let's do that. So here we multiply equation number 2 by 2, and this is our new equation. Now, we've got 2x showing up in both of our equations. So we can essentially take one equation away from another one, and we get rid of x completely. That means that we can solve for y. Okay. Now y is left on its own, x disappears because it's multiplied by 0, and we get a value for y. So y is equal to 0 makes this make sense. If we put that back into one of these equations, we can then get a value for x. So the solution for this is x and y are equal to 1, 0. Okay. That's one approach. We might also want another approach if you don't get on with the other one. So here we've got, well, it's quite similar. Another approach, we're essentially saying, okay, let's get a relationship for one of the variables. So if we rearrange our equation 2, we can get y in terms of x. So y is equal to 1 minus x. Then we can substitute that into the other equation. And essentially, with both of these approaches, we're trying to get one variable on its own so we can figure out what it is. And then once we've got one of them solved, we can get an idea on the other one. So here we've rearranged one equation, and then we've substituted that into equation number 1. That means that we've only got x in here, and we can solve for x. Get the same answer, thankfully. X is equal to 1, and then we can do the same thing. If we know what x is, we can figure out what y is. So x is equal to 1, put that in, y is equal to 0. We've got our solution. Okay. Again, useful to think about what that looks like in terms of a graph. So here's our two linear functions. What do they look like? Straight lines. So we've got y is 1 minus x. We've got that negative gradient again. We're going down. And then blue is our y is equal to 2x. That's 2. And where they intersect, we've got our coordinates. X is equal to 1, y is equal to 0. And that's our solution. That's where those two equations meet up. Just finally, because it's useful and it'll come up through some of the course, but also you'll see it in other kind of things, we've got a bit of notation to just show you. So here, the notation that we're thinking about is, what if we sum or add up a lot of things? How can we write that succinctly? So what we often do is use a capital sigma. So here we're saying, between I equal to 1 and I equal to n, summing, because that's sigma of xi, is the same thing as saying we've got this series, so x1, x2 plus xn. Okay. And we've got the same thing for products. So what happens if we multiply lots of things? Is there a nice way for us to write it? Yes. So here we've got capital pi between I equals 1 and n of xi. It's just saying we're multiplying all of those values up. So hopefully, when you see things like this, don't worry, we're not going to be working with these too much, but you can see what's going on. So essentially here, we're summing from I equals 0 to infinity of this whole function. Okay. So that's just some notation that you might come across later on. Okay. So for this part, we've gone through functions, we've gone through some common functions, and then we've started putting them into equations and solving them. and then coming down to this point about solving systems of equations, which we'll be coming back to a bit later in the course. Okay, let's end with that. Any questions on anything from this lecture at the moment? No. Okay, lovely. Oh, go on.
Thanks. I'd like you to come back on the when you were solving the. Okay, all right. So I'd like you to come back on when you were solving the exponential function.
Of
When you were solving the exponential function.
summing the exponential function.
Yeah. When you were solving the exponential
Oh,
function.
solving it. Sorry. Let me just come back to yes. Okay. So I think the key thing is when we're presented with an exponential equation, however complex or what other terms we've got going on, and you can see already that we don't need to add too many more terms for this to make it very difficult to solve. But if you are presented with an exponential equation of this form, the key thing is always to try and get your exponent on its own. So essentially we want this form. C here could be anything. Doesn't have to be a number. Could be something else entirely. But I would say before getting into the solving, rearranging so that we've got something simpler. Because we're always trying to, if we're thinking about solving an exponential, we're going to do the reverse. We're going to need a logarithm. So always aim for this. And as I said, it doesn't take much for it to be quite awkward to rearrange in that format. But as is also said, we'll be coming back to examples like this as we go into differential equations and other things as well. No problem. Any more questions at the moment? Great. Do we... What do we want to do time-wise? Is everyone happy to dive into 10 minutes of the next lecture and then we'll break for coffee? But it might split the next lecture up, is that right? Cool. Okay. Now do ice skate. Might need help navigating Apple. No, that one, yeah. And then I'll switch the screen share. Great. So because coffee is important and there will be a lot of maths, we're going to dive into 10 minutes on differentiation. We're going to have a proper coffee break and then we'll come back, finish it off and leap into integration as well. So, differentiation, moving on from functions and equations. We've already seen some differentials coming up. Oh. There we go. Yep. Clearly broken something. Cool. Okay. So through this course, we're going to be using differential equations quite a lot. You've already seen some this morning. But before we jump into differential equations and how we solve those, it's good to think a bit about differentiation itself. So we're going to revise differentiation and its applications. We're going to look at some of the ways that you differentiate, especially when you've got slightly more complex functions added together or multiplied together. And then we can look at some applications as well. Okay. So what is differentiation? With all of this, we're always thinking about how is one variable changing as another changes. And again, when you're thinking about modelling, often you're trying to capture how one thing is being affected by another, so how one thing is changing with respect to another. So we'll have something like this. This is our derivative, dy by dx. So here we've got our definition of a derivative, a little bit more notation, so we might say divide by dx, or we might have y prime. You might see both written down. This is, again, mathematicians being efficient on their notation, borderline lazy. I can say that, I was one once. But essentially, the idea behind it is we're thinking about how does y change as x changes. We can think of it as a slope or a gradient at that particular point, and we'll come back to what that looks like. Again, it's a bit easier to see when we've got a graphical representation. We can say it formally follows a limiting process. Essentially, what this means by limiting process is we're thinking about the limits of this function. So this is our definition of a derivative, y of x plus h minus y of x over h as the limit, well, as h approaches 0, as we approach that limit. Again, we'll go through how that looks in terms of a graphical representation. So it's useful for thinking about how one variable changes with respect to another. That's often what we're talking about. It also helps us find maxima or minima of functions. So if we're thinking about that quadratic function, we've got the unhappy one. It looks a bit like this. So there is a point where it changes. So we've got a kind of maximum value that it reaches, and then we start decreasing again. Same thing with the quadratic form where we've got the happy, or a is positive. We've got something that looks a bit like this. So there is a point where we reach a minimum value, and then it changes. So it's useful for finding those points, those maxima or minima of functions. So again, thinking about the graphical representation, we want to know how our variable y is changing with respect to x. We want to know how it's changing at a particular point. So you can see it varies in how it's changing. We've got a curve going on. We can approximate that by thinking about drawing a straight line at a particular point. So we might have something like this to approximate our line. This is useful because we can calculate, the difference in y over the difference in x in the same way that we get the gradient for the linear equation that Andrew showed earlier. As you can see, this is not a great approximation. This turquoise line, if it's visible, is not very close to our blue line. But if we make the distance between these points that we're evaluating on smaller and smaller, we get a better approximation of our blue line. So here, we've now got a distance of 1 in x. Our green line is getting closer to our blue line. If we make that even smaller, we get a much better approximation. Now you can see they're sort of overlapping. This is giving us a better idea of what the gradient is of the blue line in this area. That's what we're aiming to do. How is y changing with respect to x at this point? So the idea from that definition that we had earlier is we're thinking about the limit as h tends towards 0. So as this distance that we're thinking about on the x-axis gets smaller and smaller, we approach what this gradient is of the blue line at this particular point. Okay. This is a useful way of thinking about it because it's often how computer programs think about it as well. When we ask them to solve a differential equation, often they're approximating it. They're not doing it directly. So, again, we might want to think about, well, we don't want to do this from first principles all the time because someone's already done it and they've proved it, but maybe it's useful to look at some of these proofs just for reference. So, if we're thinking about what is the derivative at x equals 1, so how is y changing with respect to x at x equals 1? So again, we've got our definition of a derivative divided by dx is equal to y prime, just the way of writing it, is equal to this limit as h tends to 0 of this function. Again, we say as h tends to 0 because we're dividing by h, so we want to be a bit careful about not dividing by 0. So, we can use this definition to get our derivative at x equals 1. So here, let's take our y of x is equal to x squared, quadratic that we've seen before. And we're going to say we're interested at what's going on at x equals 1. So we can use our definition here, and we would say our derivative is equal to the limit of 1 plus h squared, that's our function, minus 1 squared, again using our function x squared, all over h. Now we've put all our values in, we can start rearranging it. And once we rearrange, we find that it cancelled down quite nicely. And here it's okay to cancel down because we're not quite at the point where h equals 0. We're tending towards it. So we've put in our values, we've rearranged, and then we use this limit as h tends to 0 to get our value of the derivative of this function, y is equal to x squared, at x equals 1. So, when x equals 1, the slope of the tangent is 2. So if we think about that curve, if we drew a straight line that only touched at x equals 1, the gradient of that line would be 2. That's what we're saying here. Okay. What does that look like? We've got something like this. So here we've got our nice quadratic function, the red line. We might be interested at different points along that line, and we're interested in what's going on at those points. So what's the gradient or the derivative at those particular points? Hopefully this is readable in the different colours. You can see here we've got kind of our x equals 1, so we had the gradient there. We've already solved that. And we can use the same approach at different points to get a value of our derivative at different points. And you can see, if we've got the tangent here, so again the line that only touches the red curve at one point, it's flat here. If we go on to the yellow one, you can see that it's got a steeper gradient, so our derivative is larger. And again, when we get to this blue line, the gradient's increased again. Got a larger derivative.
Sorry?
Okay. Yeah.
So if I get it straight, like what you are saying, when we think of derivative, is what is the duration of the curve for at a specific point?
So it's saying at that particular point, and I think this would be better to see with some other examples as well. At that particular point, how is our variable y changing with respect to x? So for a quadratic, if we evaluate the derivative at a point, we get a straight line. But if we've got a different function, we might not get a straight line as our derivative. And we've got a couple of examples of that later on. So hopefully that will better answer your question.
Okay.
A bit later on.
Good. All right. One more question.
Yeah.
I just want, we talk about the maximum and then the minimum. So why would one think of computing the maximum and the minimum? If I compute the maximum, what next? What does that imply?
That's a great question. So it depends on what you're using your equation for. It's useful a lot on optimization problems. So let's say you've got an economic balance between a characteristic that's, well, essentially you want to optimize your value. So you've got something pushing it up and something pushing it down. You need to reach a balance. There might be an output that you want to maximize, so maximizing profit or benefit from a particular thing that you're exploring through your model. And that's where you might want to maximize this function of your profit or the particular thing that you're modeling. Again, a bit easier to see with examples, and the same with minimizing. So for example, if we're thinking about infection control, we want to minimize infections. So we might have a relationship that we describe with our equations, and we can use differentiation to get an idea of where the minimum occurs, given our particular constants. For that. Okay.
So to zoom out a little bit, a very common thing we do as mathematicians. Mathematicians are fundamentally the laziest people on the earth.
I was trying to tiptoe around that, but yes.
We hate learning how to solve a new problem.
Yeah.
So once we know how to solve a problem, our favourite thing is to turn other problems into the problem that we know how to solve. Okay? So finding a maximum and a minimum, or finding the values of a function which are equal to 0, or something that mathematicians have studied for hundreds of years, and we have lots of techniques to do it. So often when we want to do something, we think, well, can we just make this into a problem like that? And then we know the solution. We don't need to find another one. Okay? So a lot of this early stuff, you know, we for the maths and computing, we could do a whole, you know, semester to cover everything you might need to know. But we can't do that. But we can remind you of these really important things which in school courses and in taught courses, they often feel like things that you are just being taught so that an exam can be set. And to an extent, that's true. But there's a hidden reason that when you actually want to do something useful with maths, being able to do these things and being able to identify, oh, this looks like that sort of problem, that's the superpower in using maths. Okay, so this can seem a bit abstract, but we'll come back and we'll use these ideas later.
Oh, I've got a question.
Maybe just to be able to contextualize your comments, just how to make meaning out of your statements. So by implication, what you're saying is that the solution to whatever differential equation you're trying to apply to a problem, it actually depends on what you're looking to do rather than one specific optimal solution that you're trying to do. For example, here you have 3 tangents where you're choosing one to apply in one situation rather and not the other, although you have 3 solutions, but you're not specifically saying that for all problems you apply one optimal solution to all of them. Did I get it right?
I think so. And I think this is, as you're making the point, it depends on your particular interest. So let's say we're going back to minimizing the number of infections, which for some reason are described by a quadratic equation. So we can find the minimum down here. We can also think about actually, currently this week, we're about here in terms of infections. So what does that mean in terms of how are infections changing? Those are already 2 different questions. What's the minimum number of infections that we can get, and how is it changing this week? Even with quite a simple equation or a simple setup, you can start answering a few different questions. But as we come back to, you set up your equations given the questions that you want to answer. So yes, whilst we've got 3 tangent lines, as you were saying, what we can do with this might vary on the problem, and we can often do more than one thing, but it might not be designed for it. So, great. Should we have a coffee break and then come back to this? Brilliant.